Okay, in this video we're going to go over the distance formula. So this is a really useful formula to use in coordinate geometry. There are a lot of different applications for it. But real basically what it is it's an application of the Pythagorean Theorem that's going to help us to get the distance between 2 points. So if you don't know what the Pythagorean Theorem is, that's okay. But if you do, it's a good connection to make, and we'll do that at the end here. But basically, this is the distance formula as it stands, so you're finding the distance d between 2 points. So if we take 2 points on the coordinate plane, let's call them point 1 and point 2. What we're using is the x-coordinate and the y-coordinate for each of these 2 points. So point 2, we would have x2 and y2 as our points, whereas point 1, we would have x1 and y1 as our coordinates. So these are the numbers, the x and y coordinates of each of these points respectively. These are the numbers that we're going to use in the distance formula. So x2 minus x1, we're going to take x2 from point 2 here, and we're going to take x1 from point 1. And then for the y coordinates, we'll take y2 from point 2 here and y1 from point 1. So we're going to plug in whatever these two numbers are. These would be obviously real numbers in real life. We could find, right, point 2 if we go over, it looks like it's at 6, 6. So we would plug in 6 for y2 and 6 for x2 as well. And then point 1 looks like it's at 4, 1. So we would plug in 4 for our x1 term and then 1 for our y1 term. All right, so this is how we're going to get the numbers to plug into the distance formula. It's all based on the coordinates of the 2 points that we choose. So be careful with these subscripts, right? x2 and x1, those are both using the x coordinates. So it's not like we're going to plug in one set of coordinates here and another set too. Here, we're using both x coordinates for each of the points and then both y coordinates for each of the points. So you're using half of each point up here and then half of each point over here. All right, so x2 and y2, those come from the same place, right? x2 and y2, those come from point 2 here, whereas x1 and y1, those come from point 1. All right, so that's an important distinction to make here. Be careful with the numbers that you're plugging in. Point 1 here gives us the y-coordinate and the x-coordinate that have the subscript of 1, and then point 2 here gives us the x and y coordinates with the subscript of 2. All right, so that's all just using variables right now. We're going to look at a couple of examples of this and really clear things up. So if we look at an example here using the distance formula, so remember I gave you the distance formula up here for reference if you want to use that. So we have 2 points here. We can label them point 2 and point 1. It doesn't really matter which is which. You're going to end up with the same distance either way. So if point 2 here has negative 5, 2 as our coordinates, that means our x2 is negative 5 and our y2 is 2, right? So this point here, what we labeled point 2, it's really x2, y2. And then this point down here, point 1, is going to be x1, y1. All right, so then by the same token, our x1 would be 3 and our y1 would be negative 4. All right, so now we have all the numbers that we need to plug into the distance formula. You need 4 numbers, right? x2, x1, y2, and y1. We now have all 4 numbers that we need for the distance formula from these 2 points. All right, so going to solve here, we're just going to plug these numbers straight into the formula. So distance equals square root, and then we have x2 is negative 5 minus x1, which is 3, squared, plus our y2 is 2, minus our y1, which is negative 4. And then that number is squared as well. All right, so going to solve these, the biggest thing to remember is order of operations, right? PEMDAS. So what we're going to do here first is evaluate the things in parentheses, right? So we have parentheses terms here, negative 5 minus 3. That will give us negative 8 which will then be squared, and this is all obviously still under the square root. And then over here we have 2 minus negative 4, which is going to give us positive 6. That'll be squared as well. All right, so moving our way along in PEMDAS to solve this, right, we did our parentheses. Now we'll do the exponents. So we have squared terms underneath this square root. So we would then have d equals square root of 64 plus 36, right, because we square a negative 8. That gives us a positive 64, right? When you square a negative number with a negative inside the parentheses like this means negative 8 times negative 8, which is going to give you positive 64. Then we have 36 inside the on the second term and under the square root here. So we can keep simplifying this down, right? If we add up 64 and 36, that's going to give us 100. So our distance is going to be square root of 100. So then we would solve to get a distance of 10. So distance of 10 means the straight line distance from point A or point 1 to point 2. Obviously, this wasn't a perfectly straight line, right? But you get the point. The distance that we're looking for here is straight as the crow flies from point 1 to point 2. In other words, a beeline, a straight line from point 1 to point 2. That's the distance that we found here. All right, so we're going to do another example here. If you want to maybe pause the video and try this one out on your own. Here's another set of points, and go ahead and find the distance between these 2 points using the distance formula. All right, so again, if you want to pause the video, try this one out on your own, that would be great. And then come back for the answer. All right, so if we go ahead and label one of these 0.1 and one of them 0.2, then we know our x1 will be negative 2 and our y1 will be negative 1, and our x2 will be 4 and our y2 will be 5. All right, so we have all the numbers that we need to plug into the distance formula here. So when we go to solve this, we're going to just plug our numbers straight in. We have distance equals square root. Our x2 is 4 and our x1 is negative 2. That's squared, plus we have our y2 is 5 minus our y1, which is negative 1. So as you can tell from the last example, you want to be real careful with your negative numbers, right? We have minus a negative here that turns into a positive, and be careful when you're squaring negative numbers as well. You gotta really watch your order of operations and your positive and negative signs here. So if we go to simplify this down, we'd get the distance is 4 minus negative 2 would give us 4 plus 2, or 6. We'll square that. Plus 5 minus negative 1 would also give us 6, and that would be squared as well. So then we can keep simplifying our way down. We would have 36 plus 36, or square root of 72. Okay, so once we get down to distance equals square root of 72 here, technically we could be done, but really the best practice here would be to simplify this radical down, right? So if we break this radical down into square root 36 and square root 2, then we can say that the distance would be 6 square root of 2, right? When you break down a radical like this, you want to break it down into something that's a perfect square. 36 is a perfect square. We break that down to 6, and then the square root of 2 just comes down because that can't be simplified any further. All right, so our final answer here, distance is 6 square root of 2. So again, that's giving us the straight line distance, a much better straight line that time, between point 1 and point 2 on the coordinate grid, right? So hopefully you're getting the hang of the distance formula now. This was a little bit more complicated an example just because we had to break down a radical at the end, but really it's the same process. Figure out what your coordinates for your 2 points are, label your x2 and y2 and your x1 and y1, plug them into the formula, and then just simplify down and solve. This is just a lot of algebra work here, so just be careful with all your math. So hopefully you're really understanding the distance formula now. What we're going to do, hopefully to nail it home, is connect the distance formula to the Pythagorean theorem. So if you're not familiar with the Pythagorean theorem, what it tells us is that in a right triangle, the squares of the two legs equal, the sum of the squares of the two legs equal the square of the hypotenuse. So if the hypotenuse of this right triangle is C, and we have sides A and B, then in any right triangle this is the case, A squared plus B squared equals C squared. All right, so that's all the distance formula really is, and we're gonna kind of break this down and compare the two. All right, so if we look at the Pythagorean theorem, it looks kind of similar to the distance formula in that we have a couple of squared terms here, and it doesn't quite look the same yet, but if we take the square root out of this side of the equation by squaring both sides of the distance formula, we would then have distance squared equals x2 minus x1 squared plus y2 minus y1 squared. All right, so if we rewrite the distance formula like this, all of a sudden it looks a little more similar to the Pythagorean theorem, right? We have the sum of two squared terms giving us a third term, and we have the same thing here, two squared terms, the sum of which is giving us this distance at the end. All right, so let's break this down a little further. If we go ahead and look at these 2 points down here and make a right triangle out of them, then we could say that based on the Pythagorean theorem, if we label this side A, B, and C, then A squared plus B squared should give us C squared. So we could find the distance of side A by just subtracting the x coordinates of this triangle from each other, right? So we have from 1 as our x coordinate going to 4, so that means we went over 3 in the x direction. And then in the y direction, we went from 3 up to 7, so we went up 4. So by the Pythagorean theorem, we could say that A squared plus B squared equals C squared, or 3 squared plus 4 squared equals, and then we could figure out what C squared would be. And if we do this, we would have 9 plus 16 equals C squared, 25 equals C squared. So this would give us C is 5 for our distance, right? So using the Pythagorean theorem, we could find the distance here. We could also do the same thing using the distance formula, and I'll switch to blue here. Hopefully, I know it's getting a little crowded. Hopefully keep this straight. So if we use the distance formula here, we have distance squared equals x2 minus x1 squared plus y2 minus y1 squared. We've gotten rid of that square root again by squaring both sides of the equation. So if we do x2 minus x1, what that's going to give us is 4 minus 1, or 3. So all we've really done there, and I can put the squared term back in, right? All we've really done here is done the same process that we did with the Pythagorean theorem down here, finding the length of this side of the triangle. And all we've done now is done 4 minus 1 to get that same result, or 3, for the x distance for that leg of the triangle that we're making. And we could do the same thing in the y direction, right? Here I'll fill in the rest of this equation. So we could do the same thing in the y direction, y2. If we, again, label this 0.1 and 0.2, y2 would be 7 minus y1, which was 3. So that gives us 4. And now we have d squared equals 3 squared plus 4 squared. If we think that matches up down here when we were just plugging straight into the Pythagorean theorem, right? We ended up with 3 squared plus 4 squared equals c squared. So here we're calling the distance d, but in the Pythagorean theorem we call the distance c, but really the process is the same. All the distance formula is we took the Pythagorean theorem, we rearranged it, and now we're going to plug in our numbers to get our distances. All right, so we could do the same thing here. I'm not going to simplify the rest of this out, right? We would end up with d equals 5 again as well, by the same mathematical process that we did down here solving the Pythagorean theorem version that we did. All right, so hopefully you can see that the distance formula here is really just a special, specific version of the Pythagorean theorem that's applied to the coordinate plane. All right, thanks for watching this video on the distance formula. Hopefully you're seeing the connections between the distance formula and the Pythagorean theorem, but if you can plug in numbers into the distance formula to find the distance between 2 points, then you're really doing okay at this point. Thanks for watching, and I'll see you in the next one.